In the previous lecture, we discussed how superconducting circuits host qubits. In this lecture, we will overview quantum dot qubits, or the qubit technology using spins of electrons trapped in semiconductor quantum dots. We have discussed in great detail how we confine electrons in a quantum dot using electrostatic gates, how we detect it, the physics and technologies of double quantum dot, and all these topics we have discussed in great detail in a couple of previous modules. So this lecture will be an overview of the technology, just to give you a feeling of the topic. So we know that these quantum dots are artificial atoms, artificially confined electron systems, and the states of these electron systems one can use to host qubits. That is the underlying idea. This view graph, the slide, is telling you that in this few electron regime, the quantum dots are artificial atoms. You can assume more or less a parabolic confinement for the gated quantum dots defined on two-dimensional systems such as aluminum, gallium arsenide heterostructure, or silicon germanium heterostructure. And the energy levels are described by this equation. In the few electron regime, they can obey some sort of shell-filling sequence for electrons. And this shell-filling sequence depends on the details of the confining potential that will depend on the design, gate voltages, and all other aspects, which we are not going to discuss in great detail now. The idea here is similar to the superconducting circuits. The quantum dots are also artificial atoms, which has discrete energy states. And one can use these states to store and manipulate quantum bits of information. That is the idea. Now, this is just to give you a feeling. This also we have discussed. So you have some sort of two-dimensional electron system. Say, for example, it could be gallium arsenide, aluminum gallium system. And when you apply voltages on lithographically defined gate patterns on the surface, you can confine electrons in the middle. And roughly, we can assume that there is a parabolic confinement for the electrons at the center here. And you can tune the gate voltages on any of these gates. And you can go to few electron regime by making this gate voltages more negative. Okay, and eventually you can empty the dot. With the help of the charge sensor on the side, which is a quantum point contact, this also we have discussed, you can detect the electron configuration of the dot or charge state of the dot, and the other temporal parameters of electron tunneling events too. Anyway, so that you can detect by looking at the signal of the QPC or the current of the QPC. Whenever that current abruptly changes, that correspond to an electron tunneling event into or out of the dot. So now what you have is, you have a system where you can trap electron, and you also have other bells and whistles to detect the electron tunneling events and the electronic configuration of the dot. So based on this framework, Loss and DiVincenzo proposed that the spin states of electrons trapped in these quantum dot, these gated structures, can host qubits. So the important point is, these are gated devices. So it's a scalable architecture. That means if you have a wafer which is large enough, you have lithographic facilities which are provided by the microfabrication technology. You can make n number of these quantum dots, and each of them can host bits of information, quantum information. And you can do spin states. You can apply field, and you can use a spin state of the field, the Zeeman split states of the spin states in the field, the Zeeman split states of the quantum dot, to store information. That is the idea. And this is an artistic view of how you have, how this storing, how this architecture is going to look like. You have an array of electrons trapped, and you have readout devices such as a quantum point contact for each of these. Okay, so that is the idea. This is proposed by Loss and DiVincenzo. So based on this proposal, there are mainly two kinds of quantum bit or qubit architecture. So what Loss and DiVincenzo told initially is, you have these quantum dots, you can store one electron in the dot, and you can use the spin state of that electron to store and manipulate information. That's what the idea in a nutshell. Now, if you look at the DiVincenzo criteria for practical implementation of quantum computer, which we have discussed in one of the previous lectures, you need to initialize the state. You should be able to address each of these bits. You should be able to read out the state and long decoherence time. These are the main criteria. So if you look at this architecture, each of these dot can be controlled by voltages. These gate voltages, which you can control very fastly by pulse, gate voltage pulses. And you can read out the state by using readout devices such as quantum point contacts or single electron transistors, or there are even more faster readout devices. Okay, so you can read out the state of the qubit. So we have two of these are already taken care, and you should be able to do 1 and 2 qubit operations. This thing we will not go into great detail in this lecture, but that is also possible because you can couple nearest qubit. So you can do operations on this, and you can also couple nearest to qubits here. Okay, so you can do 1 and 2 qubit operations. And long decoherence times, because generally spins have much longer decoherence time compared to charges. Okay, and that also we will discuss how long. Long means how long, that we will discuss in one of the coming slides. Okay, now as I told, there are two different architectures. The first one is actually called LDE qubit or Lowe's DiVincenzo qubit. That is the initial proposal. The idea here is these are individual quantum dots hosting one electron in each, which you can represent like a simple parabolic well, just one electron trapped, and you apply magnetic field, and this state will split into two states, up and down. And the separation between these two states is given by an energy scale G mu B into B. So G is the G factor, Bohr magnetron, and B field. And these two states can be, the interaction between these two states can be turned on by applying a voltage, by applying a electromagnetic radiation of appropriate frequency, which is usually in the microwave range, h bar omega, which is equal to G mu B into B. So you can turn on this interaction between these two. Okay. Now, that is the idea. So you have two states, up and down, and they are well defined states, and you can turn on the interaction by applying, electromagnetic radiations of appropriate frequency h bar omega. And if you look up, silicon has a G factor close to 2, gallium arsenide has G factor close to 0.44. There's a minus sign also here. So what that means is the energy splitting between these two states will be more, almost like 4 to 5 times more in silicon compared to gallium arsenide. So what that means is you can get appreciable energy splitting even at a much lower field for silicon, which would work in favor of silicon. There are a lot of elements which works in favor of gallium arsenide also. But on an average, in total, what you would find now is the entire technology is moving towards silicon, not towards gallium arsenide, for various reasons. And also the configuration spin up and spin down also will change because there is a sign change of the G factor also. So that also will change. Okay. In any case, you have two states, 0 and 1. You can turn on the interaction using electromagnetic wave pulses, which is like you're rotating the spin. That's what you're doing, up to down or down to up. But you can also put in a superposition of up and down too. That is the essential idea of quantum information processing, which I'm not going to mention much here, but that is the whole point. Okay, that is the core of the idea. Okay. Now, this architecture is called Lowe's DiVincenzo architecture, LD qubit. Okay. Now, the second approach, which is also equally pursued, is called singular triplet qubit or ST0 qubit. So in the previous architecture, we had one qubit, one physical qubit located in one dot. Okay. But now in this architecture, what you have is you have two dots making one qubit. If you have two quantum dots with one electron each, we have learned that they can actually, these two electrons can be in a single state or in a set of triplet states. So single state is given by this, one electron here, that is one single state. There is also 0 to single state, that is a single state of the single dot. Okay, that is not what we are looking at here, but that state is also involved in the whole this information, this manipulation. But the states here are 1 single state and T0, that is 1 this triplet state, this one. Okay, they are pretty close in energy. If you look at, they're very, very close in energy. And when you apply field, only these two will be aligned and these two are different. Okay. Now, if you look at the stability diagram, remember this is not a single dot, now it's a double dot. It's two dots giving you 1 qubit. In the previous case, in the LD qubit case, what you had is 1 dot giving you 1 qubit. Now 2 dot is giving you 1 qubit state. The idea here is this 1-1 singlet and 1-1 triplet that you assign as 0 and 1. 1-1 singlet is 0 and 1-1 T0 triplet is 1. And if you look at, there is also a small asymmetry in the charge distribution, which you have to look detail into the wave functions of these. But there is a small asymmetry. That means charge is more, tilted towards 1 dot. So that is an added advantage, because you can distinguish that also by doing a charge sensing which state it is. But that's not how you read out, but that also will give you some knob to know the state. Okay. Now we have 0 and 1 as a singleton triplet state. And if you look at the charge stability diagram, it's a double dot, right? So we have double dot as a honeycomb charge stability diagram, and your qubit is located in this region, 1-1. Your LD qubit is somewhere here, because only 1 dot you use. This only state is in 1 dot here. The state is spread in 2 dots, between 2 dots. Either this state could be a 1 or this state could be a 0, depending upon whether you have a singlet or this is a single state or a triple state. So these are the two architectures. One is LD and another is ST0. Okay, that is, in short, that is how they are known. Now let's look at over the years what are the various configurations the this gated corner dot system has gone through. So these are one of the earlier designs where you have gates and source and drain here, and when you apply voltages on all of this, you get 2 dots. Okay, but there are no readout device for this one. So this is okay if you are measuring current through the device. But remember, when you go to few electron regime, the current through device is very, very small, and you cannot use current as a readout probe. Secondly, you don't want to read out using the current, because your information is encoded in that electron, and you don't want to lose that electron. Because when you run a current, you will replace that electron with another electron. That is how the current is going to run, because these are single electron devices. Okay, so now you need a readout device integrated to the system. For example, a quantum point contact or a quantum dot. Let's say quantum dot is a single electron transistor. So if you look at here, this is a lot more compact. So you have source and drain and 2 quantum dots, and you have a readout device on the other side. Either this one or this one you can use to read out. This is a slightly different different kind of design compared to this, but the conceptually they are same. You have 2 dots and you have 2 sensors. Okay. This is slightly different design where you have 2 dots here and you have quantum dots here, because you have this will make a quantum dot, this also will make a quantum dot. If you energize all these gates, or if you energize only this or this, then this will give a qubits. So you have a lot more options here. We have quantum dot 1, quantum dot 2, then you can run whichever way you want the currents. Okay, and if you energize only this gate and this gate, you will get a quick QC, or if you energize all the gates, you will get a big quantum dot for sensing. So that is like a single electron transistor. So you have a lot of options here. And this is slightly a different variation again. If you look at, instead of 2 dots, there are 4 dots actually. If you can energize all these, you will get 4 dots, not 2. Okay. Now, when we come to here, this is actually a silicon quantum dot. Now silicon germanium quantum dot. All these whatever we have discussed, these are all gallium arsenide, aluminum gallium arsenide quantum dot. 1, 2, 3, 4, 5. There are various there. If you look at the literature, you will see a lot of variations of these designs. Okay. But now when we come here, this is now a silicon germanium quantum dot, or a gated quantum dot defined on a silicon germanium system. They also have gone through a lot of iterations of designs like here. Okay, this is one of the first ones where you have a kind of thin strip which is etched down. Then you put two gates. These are the barrier gates on the top of the edge. You can think of it like thin ribbon shaped region with a half a micron or 300 to 400 nanometer wide source and drain, and then you put two gates on top and you apply voltages so that you get a quantum dot in the middle. You can increase the number of these gates and you will get more and more quantum dots. And you have another side gate which is the 2 deck itself. That's the gate which you use to change the electrostatic potential of the dot. Very lately, you have designs where you follow the MOSFET architecture, and that is the latest thing, and that is looks like that is where now it's everybody has zeroed down to in terms of design, because of its compactness, scalability, and very closeness to the industry, where this is on silicon, and if you do MOSFET design, the industry can adapt this very easily. Okay, so there's a lot of that is one great advantage of silicon over gallium arsenide, because industry knows pretty much everything about the material. So here, what you have is you have undoped wafer. So there is no dopant layer. Okay, so that means when you start, you have no carriers. Then what you do is you have two sets of gates, overlapping gates. The green ones here and the red ones are. Okay. The red ones are used to populate the channel. That means those are the enhancement gate. You enhance the carrier. The green ones are depletion, or they are meant to create barriers. Okay. So a combination of these two gates, you can get a potential well which looks something like this. Again, two parabolic well. And the coupling between these two states and the size, number, everything you can actually vary by varying the voltages here. It's like a collinear dot, and you have an actual picture here. So what you have is you have the red colored gates, which are enhancement gates, okay, and the green colored ones are depletion ones. Okay, so you have two channels here. There are two red channels, one here, and we have this is going to host two dots, these three barriers and two dots, and here you have two barriers and one dot. That is a larger dot that is for sensing. So you have two channels nearby. This channel will host the qubit and this channel will host the sensor. So you can look at the charge state, or you can determine or detect the charges here by observing the current through this channel. So this is a slightly larger dot because you are measuring current through it, but these are smaller dots because those are the hosts for qubit where the electrons are stuck there pretty much. Okay, so this is the latest trend in terms of design. Now, looking at again the DiVincenzo criteria, you should be able to initialize and read out the state, both initialize the state and read out the state. So now we are talking about spins here, okay, not charges. How would you read out a spin? The magnetic field due to spin is really small, so you cannot detect the field due to that. So you need some other technology where you can, project the spin information onto some other degree of freedom. What you do generally is you always read the charge state, not the spin state. But somehow these charge state and spin states are coupled. Okay. So in this landmark paper, what they have done is you have a quantum dot. By energizing these gates, you get the quantum dot, and you have a quantum point contact here as a detector. This quantum point contact can actually tell you when the charge state of this dot has changed. So idea here is you apply voltage pulses to this one of the gates. In this specific experiment, the gate is labeled P. Okay. Now you can tune the level such that one of the Siemens split level is populated, another one is empty. Because when you apply magnetic field, the state will split into two, E1 and E2 here. Okay. So you have before the field, these two are same, but the moment you apply field, you have a splitting here. Now, whenever electron tunnels, whenever no electron tunneling even happens, the charge state of the dot is going to remain same. What that means, the current through the sensor will remain the same. That also will not show any change. Whenever there is a tunneling event, the charge state will change. Sensor current also will show the reflect that change by exhibiting a sudden change in the current, up or down, depending upon whether the electron is traveling in or out. That is the idea. This also we have done, okay, in detail in the previous lecture. Now let's look at a pulse sequence. How does this work? So you want to initialize the state first. Okay, so you have these two states as your 0 and 1. Okay, 1 and 0. You assume this is 1 and this is 0. That means you apply, this is your pulse shape, whatever you are doing. Okay. And the quantum point contact current is also going to respond the same way, because the pulse is an electric field. A voltage pulse is going to create an electric field at the channel of the quantum point contact. That also will reflect the same thing. So this solid line here is a representation of what you would see in the quantum point contact. Okay. How the current is going to change the quantum point. This is a representation. Actual data is here. We will analyze that in a minute. The Fermi level is here. Okay, you have two states. You take the voltage down, both of the states will go up. The dot is emptied. Now no electrons in the dot. Now the next step is you take the pulse high. That means level will be pulled in. Okay. Now when both of these levels are pulled in, you have two choices. Either this level gets filled or this level gets filled. Okay. Now, if this level is filled, now you change the pulse a little bit. Okay. Now there is a small detail here. When this one of the level gets filled, either one, the current will drop a little bit, because though the quantum point contact current is high, but the electron jamming event into the dot is going to reduce the current a little bit. That is what this drop is. That is what this drop here is. This drop here is. So this is going to fill. This signals the filling of the dot. Either way, you could either at this level or this level, that the quantum point contact cannot distinguish, because it just detects the charge. So either charge is in this state or charge is in this state. So you have charge on. Now what you do is you wait some time so that you give enough time to get it filled. Now what is next? The next is you drop the voltage halfway through, so that one of the level is above the Fermi level, other level is below the Fermi level. So if the electron was in this state, what will happen is you would have this electron tunnel out. Electron tunneling out there is going to give a signal. It's going to give you a rise in the quantum point quantum current. Okay. But now immediately, since this electron was here, it has tunneled out. Now this state is below the Fermi level, this state can get occupied. Okay. That is going to again bring the current back to the original. So the electron tunneling from the upper level will have the point contact current go up, but another electron tunneling back into the lower level will put the current up. So that is what this thing is. You have here electron tunnels out, then another electron tunnel in. That's what it is. Okay. And this stays here. But if I go through this path, say the electron was here initially itself, it occupied this state, then no event will happen even in this halfway through position. So it will be flat because nothing is happening. This is due to electron tunneling out and another one tunneling in. That is not going to be here. Now when you go to initial position again, that is the same position here, empty, this electron will tunnel. That is going to give you, if the electron was here, it will tunnel out, then that's going to give you a small increase in the current of the sensor. You just need to remember only one thing. Electron tunneling out will give you a rise in the QPSC current. Electron tunneling in will give you a drop in the QPSC current. That's it. So now what you have done now is, depending on the spin, the spin was down, then you will get a signal here. The spin was up, you will get a signal here. You are just measuring the charge and you are detecting the spin now. That's what you are doing. This is your cycle. Once you do that, you know what is the spin state of the dot. The spin was up, you will get this small thing here. The spin was down, you get this one here. That's what it is. Okay. So you get, but in both cases you are here, you are getting this one because the spin was up, but another electron was tunneled in, so that need to be emptied. That will get emptied towards the last lap. That is what you are seeing here. Okay. In either case, you will empty the dot in this segment. Okay. So what you are doing here is, you have detected the spin information, you have read the spin information of the dot just by measuring the charge. So this is one way to read out. This is spin readout by spin to charge conversion. That's what you have done. Okay. Now there is another way to do the spin information. That is also a spin to charge conversion technique, but this uses Pauli's exclusion principle. So let's look at the case of a singlet triplet system. That means it's a double dot. Okay. A double dot is characterized by a honeycomb charge stability diagram. And spin blockade, we have done in great detail that what you have is, you have a stable spin here in a double dot system, and when another spin tunnels into this dot, and this spin can actually form a singlet or a triplet state for this combined system. If that spin is down and this spin is up, then that's a single state. If it has formed a single state, then it can tunnel back. It actually can form a 2-0 state or 0-2 state, depending upon which direction the current is flowing, which segment of the which shell, which honeycomb you're talking about. Okay, 0 to 2 0, it doesn't matter. Okay, now that means if you have single state can form a 2002 state. If the initial spin is spin up parallel to this spin, then it is going to form a triplet state. Then that cannot form a 2-0 state here, or a 0-2 state in the discussion what we are trying to say. Okay. So what that means is this spin information is now encoded into the charge information. If it forms a 2-0 state, that means it was single state, or 0-2 state or 2-0 state, depending upon which direction we are talking about. If it doesn't form that single state, that means the initial state was a parallel state. Now the anti-parallel state is a 0 state, and parallel state is a triplet state, or 1 state, 0 and 1. Those are your qubit states. Now let's come back to here. So this is my qubit. Say if this is a triplet state. Now what I can do is, I can, by changing the gate voltages, I can quickly take the system to this configuration. Gate voltage corresponding to this configuration. I can change VL and VR and bring it here. But now, when I bring it here, the question is, would it form a 0-2 state or not? Okay. This is a 0-2 configuration. This is a 0-2 charge configuration. Okay. And this is a 1-1 charge configuration, this is a 1-2, and this is 0-1 charge configuration. But now when I bring this from here to here, what you're doing is you're making the well something like this. But what you would see is, since this is a triplet state, this electron cannot go here. It is stuck here itself. It's a slightly high energy state, but you cannot go here. It's blocked. And this whole thing is this transition of this electron from this dot to this dot is blocked. Okay. That means you have a sensor here. This sensor can detect whether the electron has gone from here to here or not. The sensor will not show any change in the current. That sensor will not register any event. If the sensor is not registering any event, you can say it's a spin 1, it's a state 1. Okay, qubit state belongs to 1. Now consider a single state up and down. Now when you make the same gate voltage pulse on VL and VR, because it's a single state, this easily can go to this state. So you will see it will go to a 0-2 state. In this case, it won't go to a 0-2 state because of the spin blockade. Here it will go to a 0-2 state, and in that case, the sensor will register a signal. It will tell you, okay, it's a 0-2 state. So what you are doing here is, you are reading the 0 and 1 state of a single triplet qubit just by using this sequence. So you do your operation, and if finally you want to know what is the state, you just do this transition and look at the signal from the sensor. If it is saying, okay, I have a 0-2 state, then it's a singlet. If it is saying, no, you don't have a 0-2 state, then it's a triplet. So that's the spin to charge conversion technique which is used to measure the 0 and 1 states of a single triplet qubit. The earlier one was actually for a LD qubit. This one is for a ST qubit. But earlier one also you can read out if you have an ancillary or an auxiliary dot, then with that dot you can form a single triplet state. There also you can use this spin to charge conversion by spin blockade technique. Okay, so this is how you read out the state. Now we have discussed the basic DiVincenzo criteria how those criteria are satisfied for a semiconducting quantum dot qubit system architecture. One of the main criteria is probably very, very important, is the coherence time, long coherence times. And if you look at gallium arsenide system, a lot of initial developments, groundbreaking developments, a lot of interesting physics and prototyping has happened in gallium arsenide quantum dot. It's a beautiful material system, such an easy system to work with, very clean, high mobility. It's such a beauty. There's no question on that. But it has one issue. That is, it has very, very short spin coherence time because of the nuclear spins present in the system. That slowly varying nuclear field is going to decohere the electron spins. That is exactly where silicon as a wonder material steps in. For silicon 28, it's a natural isotope, which is 94 to 95. I don't forget the exact number, but more than 90, close to 95% of the natural silicon is silicon 28, and the rest of the few percent is silicon 29, which has nuclear spin. So you have natural silicon that is close to 5% of silicon 29, and isotopically purified silicon, which is almost silicon 28 with a few parts per million. Okay, so these coherence time measurements were done on that, and you can say the hundreds of microsecond in this isotopically purified silicon for T2. T2 is an important parameter, and the qubit manipulation rates, okay, megahertz is actually less than 1 here, but it's 5 here. You can see that there's a huge jump whenever you, even a few percentage of change in the spin concentration, you can see that there's a huge jump in all these time scales. Okay. So on top of that, silicon is combined with CMOS technology. The industry knows pretty much every bits and pieces of silicon, how to process it. This is such a almost like a half a century old industry, multi-billion-dollar industry. It knows pretty much how to fabricate, how to make the material, how to make the wafer, how to fabricate the device, everything. Okay. On top of that, it has superior spin coherence properties compared to gallium arsenide. So the current trend is everything towards silicon. Now, as I told, the industry can directly adapt the technology from the prototyping labs. So the labs also have stepped up the scaling exercise of these qubits. So this one is for a gallium arsenide. Just want to mention there are a lot of works going on in that. So this is a 4-qubit system. There are 2 sensors also here. This is MOSFET enhancement mode architecture quantum dot, and this is using same design. This is like a 9-qubit register. There are 9 of these qubits here, and there are 3 sensing devices made in silicon. And this one is called a crossbar geometry. This is a new proposal where you have 3 kinds of gates here. There are gates, red gates and the blue gates defining the barriers, and you have these gates defining the dots. I mean, define the position, which dot you want to populate, which region you want to populate, and by pulsing these gates, you can also change the overall configuration. Okay, and there are also readout devices and other thing, lot of other things. We can go through this paper. It's beyond the scope of this lecture. I just want to summarize here that now finally, recently, Intel has come out with a wafer scale production of wafer scale full of qubits only, large wafer. So that is the current status. It's a very fastly evolving field, and this what I have tried here is to give you an overview from start to the current stage. So current stage is silicon qubits, which are hosted in silicon germanium or silicon dioxide, similar to a MOSFET. This is scalable by the industry. Now the challenge is how to control this, how to scale it, how to control this, address it, read out it, and how to basically, there is one important point which I have not mentioned, that is how to couple these spin states to other spin states which are distant, located somewhere else on the wafer. So you can use some kind of bus electromagnetic waveguide, planar waveguide geometry buses, where you need to couple the spin degree of freedom to the cavity modes. That is the current, the current focus of research. All right, thank you.